So atomic line, spectra, and Niels Bohr. So light is separated into its component wavelengths by a prism or diffraction grating. So, or sorry, I shouldn't have read that in that order. So this is a way of obtaining these atomic line spectra. So these individual lines. Here is the spectrum which is observed. And so there are only a few of these for each element, and they kind of form like a fingerprint for the element. They correspond to these transitions between the orbits. So here we have what's called a gas discharge tube, which just contains a gas such as hydrogen. You could also have neon or whatever. And this then has an electrical current pass through. So it has like these two electrodes, and then an electrical current is put through this system. This electricity then excites the hydrogen in this case, and then it doesn't like to be excited, so it loses some of that energy and relaxes down to the ground state. And then this relaxation, it's absorbed the energy in the first place to become excited, so it has to release that energy in order to go back to the ground state. And so when it goes back to the ground state, it releases the energy as light, and so this can then be concentrated using these narrow slits. And so we end up with a very thin beam of light, which is incident on this prism. And then as the light passes through the prism, it is diffracted such that it is split up into its individual components. So it kind of looks pinkish here. And so this pinkish light then corresponds to like a red line, a green line, a cyan line, and a blue line. And different elements have different fingerprints. So for example, hydrogen has about 4 that we can see in the visible range between 400 and 700. There are also some that we can see in the slightly UV, because our eyes can also see a wee bit into the UV, but only a little bit. And then mercury then has a lot more lines. They are usually quite different from those of hydrogen. They correspond to those transitions between the orbits. And then neon as well has a different fingerprint. Some of the lines are similar, but ultimately there's enough of them that are different that you can form a fingerprint. It's like, you know, our fingers, our fingerprints, some of them have maybe similar lines to other people, but whenever you put the whole thing together, you'll see that each one is more or less unique to each person. And so these lines for hydrogen and hydrogen-like elements or particles were described by an empirical series. So they're empirical, so it doesn't necessarily obey the theory perfectly, but this series called the Balmer series was observed 30 years before it was explained. And so this happens to be only true for the transition to the n is equal to 2 level. So for example, remember we had n is equal to 1 is the one closest to the orbit closest to the nucleus. N is equal to 2 is the next orbit further out, but closer than n is equal to 3. So this Balmer series, which was observed very early on, is a relaxation or back to the n is equal to 2 level. This was observable in the visible range. The n is equal to 1 transition does also happen, but it wasn't observable in the visible range, so it took a longer time for that to be discovered. So this Balmer series helps to describe the wavelength of these lines that we observe, like in this fingerprint spectrum, this line spectrum. And so we can actually use this to calculate the values of the different lines. So for example, if we want to calculate the transition from 3 to 2 or 4 to 2 or whatever, n is equal to 4 to 2. So let's do 4 to 2, why not? Going back here like this. We have 1 over lambda is equal to the Rydberg constant, which is just a constant. I think it's 1.0. Is it here? It's not here. I'll look it up. The Rydberg constant is 1 point something. Uh, 1.096 times 10 to the 7 per meter. So R is equal to 1.097 times 10 to the 7 meter to the minus 1. Okay. Then this is then going to be in here. It's going to be 1 over 2 squared because it goes, this is like initial, I, and this is final. So where it starts and where it ends in the transition. So it always ends at 2. And so this is going to be minus 1 over, since we're doing 4 to 2, it's going to be 4 squared. And so that then becomes, is equal to what? 1.097 times 10 to the 7 times 0.25 minus 1 over 16. I don't know what that is. Is going to be equal to 1 over the wavelength, which this is going to be what? 1.097 times 10 to the 7 times 0.25 minus 1 over 16, which leaves us with a value of 2,056,875. Reciprocal meters to the minus 1. So then to find the wavelength, it's just going to be 1 over this value. And so we end up with a value of about 486 nanometers for this 4 to 2 transition. So let's see if we have a line that's about 486. Yes, we do. Here it is, 486, more or less. And so that's the wavelength for that transition of n is equal to 4 to n is equal to 2. So the calculation is pretty straightforward. But unfortunately, this only works for hydrogen, and it is an empirical relationship. It's not really, it doesn't obey all of the theory, because it would also apply for other systems if it did. So the Bohr model, energy is negative for all values of n. Lower or more negative values are more stable. The lowest is for n is equal to 1, which is the most stable, and 0 for n is equal to infinity. This is above the ionization energy. So we can see this is how this is distributed here. So E1 here, this is n is equal to 1. So this is the most negative energy. This is the most stable. And then as we increase the value of n, we see that we increase the energy. So this is less stable. So as we go up here, what we see is that we're gradually increasing the energy. And the spacing between these lines is getting smaller and smaller. So you can see here, this is a large gap and then a smaller gap, smaller, until we reach almost 0, which is n is equal to infinity. At this point, the electron is no longer being held very much. And so it will go off and it will be ionized. So the difference between successive energy levels becomes smaller as n becomes larger. Excited states with n are greater than 1, or states with n are greater than 1 are excited states. The energy of the electron in the hydrogen atom depends on n. The larger the value of n, the larger the Bohr radius, and the less negative the energy of the value of the energy. And here's the ground state down here. This is the most stable. So energy transitions. So ground state is the lowest energy level where n is equal to 1. Excited state is any higher energy level than the ground state. So therefore n is greater than 1. So n is equal to 2, n is equal to 3, and so on. And then E is equal to 0. The electron is completely separated from the hydrogen nucleus. So n is equal to infinity. Sorry. This is similar to the ionization energy. So the Balmer equation, which we just discussed, is a mathematical relationship among the observed frequencies. An equation was found that could calculate the wavelength of the red, green, and blue lines in the visible emission spectrum of hydrogen. It only works for one electron particles. So this is the same equation that we saw earlier. It's exactly the same. Just happens to be V. It's no longer nu. So this is the wave number, which is reciprocal meters. So the change in energy from the final to the initial. So this is the final. So it always goes back to 2, remember, for this Balmer series. So n is always going to be equal to 2 for final, or for the final. Okay. So V equals the wave number, not frequency. So this is 1 over the length, which is not that, it's meter in this case, or it could be nanometers or whatever, or centimeters. Often it's centimeters. When n is greater than 2, so we calculate the wavelength for one of the Balmer series lines, which we did earlier. We did the n is equal to 4 transition to n is equal to 2. Okay. Knowing that the Rydberg constant is this 1.0974 times 10 to the 7 reciprocal meters, or wave, or yeah. So this is a schematic. This is going to be kind of like the last thing that I'm going to discuss here of what happens. So here we have the ground state, and it is going to absorb some energy, a photon of energy, which has at least the energy difference between here and here, which we can calculate based on the Balmer equation we saw earlier for this one electron system. So it's positive here because the energy is being absorbed. We also discussed that. So here the wavelength or the energy of this photon is sufficient to enact this transition from the ground state to the excited state. And then the energy can then be emitted from the excited state back down to the ground state as delta E is equal to minus 984 kilojoules. So the energy is emitted again, same amount of energy, and it's given a minus sign, even though the photon always has energy. So it always is positive energy. It always has energy associated with it. We just give it the negative because it's releasing the energy. Okay, and so that is where we'll leave it now, and we'll pick it up next time. Thank you. All right, so this is where we left off last time with the excited state energy absorption of a particle. In this case, that particle is an electron. We learned that certain amounts of energy are required in order to have it be absorbed by the particle, or the electron in this case. So what does that mean? It means that whenever we're talking about a particle or an electron or something in the ground state, it's not good enough that we provide it with an insufficient energy to get from this ground state to this first excited state, this n is equal to 2 level. We need to provide exactly this much energy, or at least slightly more energy, and then the atom or the electron will absorb that much energy in order to go to the excited state, and then whatever's left over may be converted into kinetic energy. So what happens is that, like, for example, in the sort of macroscopic world, in our world, what we can do is if we have some sort of trailer full of goods, and one truck is insufficient to pull it, we could tandem those trucks together, or link them together in some way that they could combine their forces to pull it. It's kind of like if we were doing, if we were like trying to carry a heavy box, like one person could maybe carry it, but if we put 2 people together, then we're definitely able to carry it, something like that. You can't combine energies in that way for electrons and subatomic particles. They have to get that much energy from one source. So in that case, this light must have sufficient energy to go from the excited state to, or sorry, go from the ground state to the first excited state, or it can go to the other excited states too if there's sufficient energy. But it's just this idea that this energy must, this incident energy from the light must be sufficient to sort of bridge this gap. We say here that there's a positive sign in front of delta E. Delta E is the energy difference between the 2 levels. It's a positive energy difference whenever the energy is absorbed. and it's a negative energy difference whenever the energy is emitted, but don't think that the energy doesn't exist, like that it's negative energy. The energy is still there. It's just, this is our formalism in order to understand, or to make it easier to understand what's happening. We also talked about things like the photoelectric effect, where whenever light is incident on a particular type of metal, we're able to release electrons from that metal to carry an electrical current through an electrical circuit. And if that energy is insufficient, remember that we can interrelate the energy of the wave via Planck's equation. E is equal to h nu, where nu is the frequency, and that it can almost be related to the wavelength because of this relationship here, where c, the speed of light, is equal to lambda, the wavelength, times nu, the frequency. So it's thanks to these that we can interrelate energy, frequency, wavelength, thanks to these two equations. So we also talked about the Balmer series in detail. So it was the first one that was kind of observed because it was in the visible region of the spectrum. These series are for the hydrogen atom only. They work well for the hydrogen atom, but they're empirical series, which means that they do not necessarily totally obey theory. Rather, they're just a nice mathematical way of determining them. And we did a calculation and we saw how that's possible. So then if we want to find the energy difference between these two states, we can calculate this delta E using the Balmer equation or the Rydberg equation for each level. So if we want to calculate the energy, for example, of the green line in the hydrogen spectrum, we know that the green line involves a transition from n is equal to 4 to n is equal to 2. And so we can use an equation, this is equation 6.5 from the book, but we'll see that equation in a moment anyway, to calculate delta E for n initial is equal to 4, where n final is equal to 2. So this is a relaxation. So we're going from, so say we have a ground state here, this is n is equal to 1. Then we have some excited state, n is equal to 2 here. And then we have another state, n is equal to 3. And then n is equal to 4. So we have some electron or particle here in n is equal to 4. It's going to relax down to n is equal to 2. And we're going to get some energy released. So we want to calculate what that energy is going to be. So delta E is going to be the energy of the final level, which is n is equal to 2, minus the energy of the initial level, which is n is equal to 4. And we can use that to determine the energy of the photon, which is the absolute delta E. Obtain the energy of the photon using step 2. And then finally, we can convert this to the wavelength using Planck's equation to obtain the wavelength. Because remember that, why is it? Because remember that E is equal to h nu and c is equal to wavelength nu, which means if we put nu in here, we get E is equal to h times c over the wavelength, which can be rearranged to give us the wavelength. So wavelength would be equal to h c over E. H and c are constants. H is Planck's constant. C is speed of light. So really, if we have the wavelength, we can find E. If we have E, we can find the wavelength. Okay, so here's our equation for one of the energy levels. So, or n is equal to that principal quantum number. So for the initial level, n is going to equal 4, and for the final level, n is going to equal 2, because we're seeing an emission transition between n is equal to 4 and n is equal to 2. So in this equation, we have a bunch of constants. So we have R, which is the Rydberg constant, H, which is Planck's constant, C, which is the speed of light, all over n squared, where n is the principal quantum number. So you can see that the only thing changing here, hopefully you can see anyway, is this n value. So n is equal to 4 for our initial and then it's going to go to n is equal to 2. So yeah, so we have this equation here, but then going to fill it into here as E final and here as E initial, and that will give us E delta E. So here we have filled in those. So we just literally got this, put it in here and here, and then got this new equation here. Where n final, remember, is n is equal to 2, and n initial is n is equal to 4. Right? So this can, in fact, be simplified. So we can see that we have the same constants on the top, RHC, RHC. So we can take R minus RHC out of the brackets, or like put it outside, and then we just have this term in the middle, which is going to relate the final to the initial times some constant, which is equal to delta E. All we're doing here really is some basic algebra at the moment. And then this leaves us kind of with this equation here where we have delta E, which will give us our photon energy eventually, is equal to minus RHC, which R is the Rydberg constant, H is Planck's constant, C is the speed of light, times this 1 over n squared final minus 1 over n squared initial, giving us this. So E is equal to H times C over lambda, which we already talked about. So that's the energy can be related to Planck's constant times the speed of light divided by the wavelength. So that means we can use the wavelength to get the energy or the energy to get the wavelength. So the absolute change in energy, this is going to be equal to H times C over lambda of the photon. So we just rearrange this equation to get lambda of the photon. So here we have our equation to find delta E. This is our Planck's equation using the C is equal to wavelength times frequency. And then this is our way of finding the energy based on the wavelength of the photon, or we can just, multiply through by lambda and divide through by absolute change in energy, and we can get the wavelength of the photon in meters is equal to H times C over this delta E. So this takes an absolute value to assure a positive wavelength. The sign of delta E tells the direction, so it's either going to be positive, indicating absorption, or negative, indicates emission. So it's not this delta E, it's the delta E that we calculate here, which can be positive or negative. This always should be positive so that our wavelength is also positive. Otherwise, we would get a negative wavelength, which doesn't really make any sense. So yeah, so the positive or negative at this point tells us whether it's going to be absorption. If it's positive, negative means it's going to be emission. So here's an example calculation using those formula that we have created. So our constants here, so this, the product of our constants, R times H times C, is 2.179 times 10 to the 18 joules. We then can use this in our equation, which we have here, this nice little equation that we determined. And then delta E is equal to minus this product of our constants here times 1 over, 5 squared, which is our final in this case, and minus 1 over 2 squared, which is our initial. So here we're seeing an absorbance from n is equal to 2. N is equal to 2. Oh, it's already drawn here, sorry. Here it is. So we're seeing an absorbance from n is equal to 2 to n is equal to 5. This is the energy in. So energy in is like the electromagnetic radiation, something like that. And this is sufficient to increase the energy level of the particle from the ground state, or well, not the ground state, from the first excited state to the fourth excited state, which is n is equal to 5. So this is just like 1 over 5 squared, so 1 over 25 minus 1 over 2 squared, so 1 over 4. So that gives us a negative value here, which will mean we will have a positive value overall, and that's what we have. We have delta E is equal to positive. So the value of delta E is positive because this is an absorption. So you can see that it is absorbing light to go up here. It needs energy to affect this change from n is equal to 2 to n is equal to 5. Just be careful with your mathematics. Don't equate these two forms together. So it's always 1 over n squared, never 1 over the n squared final minus n squared initial. It's always the 1 over minus 1 over n squared, because you can get different values. So for example, this is our calculation from earlier or from the previous slide. You can see that if we do it the correct way, we get a negative value, which will give us a positive delta E, which is what we want because we have an absorbance. Whereas here, if we do it this way, which is 1 over n squared minus n squared, then we get a positive value, which means that we would have a negative delta E, which would indicate that we have an emission of energy, which is incorrect. So here is a continuation of that problem that we had a moment ago. So we calculated the energy, the absolute change in energy is going to be this. So that means we can find the wavelength of our photon pretty easily. We have H, we have C, those are both constants here and here. Then we fill in this delta E value, which we calculated up here. Here it is. And then this is going to be lambda photon is equal to this times this is equal to 434.0 nanometers. So this part here is really just the conversion factor from meters to nanometers. But the wavelength of our photon is 4.340 times 10 to the minus 7 meters. Okay. So this was all based on the Bohr model of the atom, which had, if we recall, a central nucleus, and then it had surrounding that something called an orbit. Many of them to allow all of the electrons to exist. It also had a defined distance between each orbit. So it was pretty good, I'll be honest. It wasn't terrible. It was a good model. The problems with it were that it could only really work for one electron system. So this is a system that I've just drawn, which has 2 electrons. Really should be like 3 electrons at this point, so it should be like lithium. The problem here is that the line spectra cannot really be properly accounted for using the Bohr model. So the successes of the Bohr model was that it described the line spectra of the hydrogen atom really well. It did a really, really good job of that. The problem was that it only works for 1 electron systems. So for example, it works for hydrogen, which is the prototypical 1 electron system. It also works for helium plus, which has also got 1 electron. It also would work for, like, for example, lithium 2 plus, or beryllium 3 plus, or what's the next one? Boron 4 plus, etc. Basically anything that has 1 electron, the Bohr model will work for. So just remember that. That's the limitation. But so long as you only have 1 electron in your system, you can still use it. But its success also was the fact that it was used as the basis for the model that we do use now, this idea of orbitals that we have now. So a Bohr model has orbits, but the sort of quantum mechanics or wave mechanics that we use now make use of the Bohr model, but we now have orbitals. So he won the Nobel Prize for his model in 1929, around about the time when people were starting to develop it further. So if light can be viewed in terms of both wave and particle properties, why can't particles of matter, such as electrons, be treated in the same way? So this is, I think de Broglie said this. So de Broglie had this idea that why can't we also treat electrons like waves? I mean, they have matter-like properties, but they also have wave-like properties. So why can't we give them an intrinsic wavelength, or even give matter in general an intrinsic wavelength? So here we have what's called the de Broglie wavelength. So the wavelength is equal to h, which still is our Planck's constant. M is the mass, and v in this case is going to be the velocity of the particle. So I prefer a big V, to be honest, capital V. But anyway, they put a small v. So matter has wave properties. So this doesn't really matter for us, because the way that this works is that as the mass gets larger, the wavelength gets smaller. You can see that because it's on the bottom, it's the denominator of our fraction. So if this is constant, then as mass continues to increase, then this value here is going to get smaller. So you could calculate the wavelength for human beings as well, but because it's so small compared to our size, it doesn't really have any meaning. But we still could have one. So 1 joule is equal to 1 kilogram. Oh, sorry, this is just a conversion factor here. Then Planck's constant is here, and then mass is m, and v is velocity. So how fast the particle is moving, how much momentum it has, because I don't know if you remember or if you know from classical mechanics or whatever, P is equal to mv. So momentum is equal to mass times velocity. So the de Broglie wavelength is equal to h over momentum as well, because this part is mv. So mv is equal to p. So the de Broglie wavelength can be related to momentum as well. So de Broglie, so matter has wave-like properties, not observable for big pieces of matter such as golf balls. We'll do that calculation in a moment, and we'll see that golf balls do in fact have a wavelength, but it's just not really measurable or really that important for a golf ball. But it is observable for small pieces of matter such as electrons. So the wavelength of a golf ball then. So a golf ball is quite small for us. It's a small sphere, weighs about, here the golf ball they've chosen is 82.5 grams. The velocity, if you hit it and you hit it really well, could be up to 255 kilometers per hour. So it's about 150 miles per hour. The wavelength then associated with this, if we put it into our equation, would be the equation that we had before, which is the de Broglie wavelength is equal to h over mv. If we put, because we have the mass here, we have the velocity here, h is our constant, we can find that the wavelength of this is given here. So this is very, very small. It's times 10 to the minus 34 meters. Golf ball is about what? 6 or 7 centimeters in diameter. So is it even that big? Maybe 5. But anyway, so 5 centimeters is what? 5 times 10 to the minus 2 meters. So you can see there's a huge difference between the wavelength and the actual size of the golf ball, which means that the wavelength doesn't really have much of an effect. It's a big particle, a very short wavelength. But if we have an electron, electrons are very, very small. You can see here its mass is really small, but its velocity is very large. So if we then use these values and we put them into our de Broglie wavelength equation, we can get a wavelength here, which is actually much bigger than the wavelength for the golf ball. And that's sort of a function of what I mentioned earlier, where whenever we have the de Broglie wavelength, it's equal to h over mv. So if the mass is going to be very small, then that means that this is going to be a larger value, this fraction. So it's a small particle. Electrons are very tiny, but their wavelength is no longer negligible or no longer unimportant compared to the actual size of the particle. And so what we find is that electrons actually have wave-like properties. They form something called a standing wave. So basically, they're a wave which goes in a circle around the atom, or in a well, in 3 dimensions, three-dimensional circle around the atom, but it has different sort of like peaks and troughs depending on which quantum number it has. If you go onto YouTube, you can see videos on standing waves. Standing waves are something which happen on a macroscopic scale as well, and you can see lots of nice videos of standing waves. So wave or quantum mechanics. So Taking the ideas of Bohr, de Broglie, and Heisenberg, Erwin Schrodinger proposed that matter can be described as a wave. In this theory, the electron is treated as both a wave and a particle, and so it now has to be described by something called what was called a wave function. So this combines this wave and particle-like nature of the electron, and is given the Greek letter psi that completely defines the system of matter. So basically with Bohr, de Broglie, and Heisenberg uncertainty principle, we haven't mentioned yet, but we're about to. Bohr is the Bohr model, which is what we looked at for the hydrogen system. De Broglie is what we were just talking about there, with the idea that matter could have a wavelength, and then Heisenberg will talk about it. So Schrodinger brought all of these theories together to kind of create this idea of a wave function, which can describe an electron. So an electron only has allowed energy. So we saw that with our quantization of the energies in the photoelectric effect in the Balmer series and the Lyman series and the Paschen series. So results presented, so for example, the mathematical relationship between all of these properties of an electron won Schrodinger the Nobel Prize in 1932. The wave function psi has no physical meaning, but it is the way that we describe mathematically the electron. And then the wave function squared is the probability of finding an electron in a region of space. And this is an orbital. So the wave function squared, so the wave function has some sort of wave-like shape. So the square of that is going to be, so the square of the wave function is going to be something like that, where we have these peaks, we have these troughs, and so on. The squaring really just creates this safety net that we don't have a negative probability of finding it somewhere. So as I mentioned before, electron orbitals can kind of be described as a standing wave. So this is a way that we can create a standing wave just as an individual person. So we can tether a string or a rope to a wall or a door handle or something like that. And then we can move our hand up and down. If we hold it fairly tight, you need to hold it quite tight, but not too tight. Move your hand up and down or flick it up and down, you will create this wave pattern. Now, the more energy you put into that wave pattern, the more complex the form will take. So if you do it if you hold it quite tight and you do it with limited amounts of energy, kind of like a skipping rope, we'll see that it will go up and then it will go down and it will go up and it will go down. And so this is because the energy, you're giving it the energy to go either up or down. So if you're like flicking your wrist up, the wave will go up, but then it will come to the wall at the point at which it's fixed, and then it will come back in the opposite direction. So it initially goes out with a peak and goes in again with a trough, well, a negative peak. If you increase the amount of energy that you're giving to the standing wave, you will see that you will create a more complex system or a more complex waveform. So this one with more energy now has a full wavelength between your hand and the wall. So it has a full wavelength because a wavelength starts at 0, goes through a node, and then ends at 0. So that's a full wavelength right there. This one is only a half wavelength because you can see it only has a positive part, whereas this now has a full wavelength. And remember that we can relate wavelength to energy using Planck's equation. And so then here we have even more energy, and we can see that we now have 3.5 wavelengths. So the wave motion here, wavelength and nodes quantization in a standing wave. So here we have the quantization of standing wave. All right. Now the thing is that your hand on a wall are not exactly a perfect measure for, or a perfect example of these sort of quantized systems that electrons exist within, but it's pretty good. I mean, because you can give you don't give the rope or the string exactly the right amount of energy every time. So in fact, that you end up with a system where it can have continuous changes in energy, and that's representative of a macroscopic system. But electrons exist in a quantum system where everything is tightly defined. The energy between each level is tightly defined and quantized. So from the book In Search of Schrodinger's Cat, we have a quote. So if it were possible, if it were ever possible to know the position and velocity of every particle in the universe, then it would be possible to predict with utter precision the future of every particle and therefore the future of the universe. Big words. So what this basically means is that for every particle, like electron, atom, or proton, neutron, whatever, if we were able to know the position and velocity of it, so its position, so where it is, and its velocity, how fast it's moving, or its momentum, then we would be able to predict with utter precision where it was going to go. And so that would mean that we could literally predict the future of the universe. Unfortunately, we cannot. Well, maybe fortunately, I don't know. Depends on your point of view. But we cannot do that because of something called the Heisenberg uncertainty principle, which creates a system where we cannot know both the position and the velocity at the same time, and that the energy of the particle can never actually be zero. And so if the energy of the particle can never be zero, we can never know its exact position or its exact velocity. So the uncertainty principle, then, this is the Heisenberg uncertainty principle, which is defined by that previous statement. So Heisenberg won the Nobel Prize in 1932 as part of this work. For an electron, we cannot know simultaneously both the position, which is going to be x, and the momentum, which is p is equal to mv. That's where the velocity comes from in the previous slide. So velocity can always be related to momentum if we know the mass, and since the electron's mass is well defined, we know the mass. So observation affects behavior. So this is also another key takeaway, is that if we actually observe the system, we change the way that the system behaves. So we can think about that in the way that if we have seen a mouse, either unfortunately in our home or fortunately if it's a pet, I guess, we could also see a mouse out on the street sometimes. If we just leave the mouse alone, it will carry about its business. It will go forage for food. It will try to exist basically in the form that it is. If we were to flash a light on it, like a flashlight, or to disturb it in some way by observing it in a way that it knows that we are observing it, then suddenly the mouse's behavior becomes much more erratic. It starts to panic, becomes stressed, and it moves around a lot. So that our observance of the mouse has changed its behavior. Another example is, for example,